A cement silo looks like a simple upright vertical cylinder, right? Today I will dive deep into the design of this heavy equipment and I will decipher the complexity inside. I'm Dr. Ali Reza Islami, the former university professor, and welcome to my channel, Dr. E. Hello my friends and followers. Today I will present the first episode of Design for Manufacturing, and the subject will be the cement storage silo, 28 tons in capacity. Perfect. Before starting the detailed design, let's have a quick overview on the anatomy and the details of a silo and see what is the auxiliary equipment and what is the structure of silo itself. As you can see, the silo has three main important parts: the cylindrical part, the conic bottom, and the roof deck that has a little slope to make it easier for draining the snow or rain. And then we have the ladders and the guardrails installed for supporting the technicians to climb during the maintenance and cleaning the air filters. There is one important element here is the riser, the pipe that we are filling the cement from the bottom all the way. It goes to the top and enters from the roof deck where we are releasing the feed into the silo. Once we are feeding the cement into the silo, the air should get released to the outside. But once the air is released to the atmosphere, it will also rise a part of cement like a dust. And this is where we are entrapped in air filter installed right in the center on the roof deck. This cement that is entrapped inside the air filters will release either by mechanical vibrations or with pneumatic air pressure. It's dependent to what type of system is used there. We also have a relief valve, pressure relief valve, installed on roof deck. It's important for controlling the overpressure and also underpressure, because both of them might happen during the operation or feeding the container. That might the explosion or implosion if it's not controlled properly. Then we also have a level sensor to control what is the level of cement inside and when is the time to fill it again. The air nozzles that are installed in the conic side. This is important for making sure that all the cements are just depleted properly from the bottom flange, and nothing like made glued to the walls or the conic part and bridging there. And we also have a butterfly valve that is for connecting the screw conveyor to the silo. The conveyor or the screw conveyor is the element that are depleting the cement with an electromotor to the desired spot that might be the top of the mixer. There are manholes, handholds, and also the sight glasses and other controlling elements installed to this equipment. During the detailed design for manufacturing, we will control also these elements together. Okay, let me now explain why I selected 28 tons as the capacity for our storage cement silo. Once we are ordering directly the cement from the factory, then the bare minimum purchase order that we can place there is at least one 3-axis or 4-axis bulker cement tanker carrier. That it's close to 24 or 26 tons of cement. So based on that, we are making the bare minimum dimensions for the silo to make it economically viable, and this is why we selected this volume. Perfect. Now let's we check the volumetric density and also the dimensions. For the cement, the loose bulk density will be close to 1.25 tons per cubic meter because of the entrapped air. And since we are considering 28 tons of cement, with the density that we already mentioned here, the volume should be at least 22.4 cubic meter. We will add 12% expansion space at the top that is important for compensating any changes in the pressure during the filling, especially. that we are ending to 25.1 cubic meter. And this is the volume that we will use as a base for sizing the diameter, the height, and other parameters. In next slide, we will see how we will deal with it. We will consider 10 to 15% buffer factor. Why we are considering this volume? Because once we're feeding the cement into once the truck is pumping the entire load under pneumatic pressure into the silo, then we might face the high-level alarm, we might face the chock, the top pointing filter, or maybe overpressure, under pressure. So to avoid all of these things, we better to have the safety buffer factor that is 10 to 15%. We will see that adding 2 to 4 tons extra capacity to the silo will add actually to the safety of this device. Good. I also checked the standard market sizes to see whether these dimensions and the volume or the capacity of the silo is compatible with what is in the market. And with quick cross-checking with the market, we will see that 28 to 30 ton silos are common, and the volume that we consider 25 cubic meter for the hopper bottom silo is exactly within the things that are already available in the market. So this is perfectly fit to the thing that it's standard and it's all in the market. This will ensure that it's also compatible with all the truck, trailer, handling, carrier, so we will not face any problem during the operation or finding the parts once we are manufacturing and putting everything together. Good. Okay, the first thing that we need to have after considering the volume for the silo is what is the best diameter for the shell section in the cylindrical part. And here we will consider one restriction, that is maximum width for normal loads that we can use the standard trucks beds to transport this silo in horizontal ship after manufacturing in some workshops. So we are ending with 2,500 millimeter, the diameter. This is a thing that we are considering as a now first dimensions, and then based on that we can calculate what should be the height, what is the specifications or dimensions of the conic bottom, and also the top roof deck. These are the things that are all based on this fixed number that we are considering based on the maximum truck load dimensions. So then 2,500 millimeter is the diameter of the cylindrical part. Perfect. After selecting 2,500 millimeter as the diameter for the cylindrical part, we can now calculate how much should be the height, and what should be the specifications of or the dimensions of other parts of the silo. Here for the cylindrical part, we are ending to 4,250 millimeter, the height of the cylindrical part, because the conic side should be with the angle of 60. Once we are considering all these criteria for the conic bottom and for the top roof with the slope that we need to actually to drain off the rain of the deck, so you're ending to this number. I'm rounding this number up to 4,500 millimeter. And why I'm doing this? Because the widths of the available metal sheets in the market are in a standard close to 1,500 millimeter. I don't want to have like losing material. I also don't want to have redundant metal works like cutting, CNC plasma cutting or welding. So that is why we are selecting 1,500. We are again rounding up to 4,500. This is a thing that we are adding actually to the buffer volume that we considered and I explained at the beginning of this presentation. So 3 rings, 1,500 millimeter, the height of each. We have 4,500 millimeter, the total height of the cylindrical part. Thickness of the cylindrical shell, according to the strength calculation, will be 5 millimeter. In future, we can also come to the calculations of this number, safety factors that we consider here. But as a bulk rough estimations, you just accept that 5 millimeter is good enough for these dimensions according to the standards and the things that are available already in the market. and I'm considering this number as a default for the design. And we will manufacture, of course, this storage tank based on this thickness. Great. Now we will have the summary of all the dimensions, or the key dimensions, or let's say the key dimensions of this equipment. 2,500 millimeter is the outer diameter. Cylindrical shell height is 4,500 millimeters. The deck roof height 320 millimeter. The height of the 60-degree conic bottom will be 1,800 millimeter, and the distance between ground floor level to the opening of the conic bottom will be 1,500 millimeter. And as I mentioned at the beginning of this presentation, when I was explaining the anatomy of the cement silo, I explained that this is according to the standard conveyors, screw conveyors, and the maximum inclination angle that is acceptable with these conveyors to have the maximum performance and to have the minimum electrical energy consumption. Otherwise we will end up with either stocking the cement inside the conveyors, or we will end up with a lot of energy consumptions and heat up or temperature rise inside the conveyor. So we should avoid to do that. Okay, since we are designing for manufacturing, we here need to also have a look into the material that is available in the market. I will use the hot rolled steel coil, HRC, that are actually sold by the factories in big coils from the 15 to 25 or 22 tons per coil. And here we have one couple of big advantages. First of all, these HRC coils are cheaper comparing to the flat sheet metals. The second is that we don't need to be restricted within the limited lengths that we have normally for such these flat sheets of metals. Why? Because sheet metals are normally coming in standard lengths: 3 meter, 6 meter, 9 meter, 12 meter, and once the length is increasing, the price and cost for that also increases. But with the hot rolled steel coils, first of all, we have good ductility for any kind of cutting, grinding, milling, welding, and we are not facing any issues here. There is also like a memory for the coiling, because these are the things that are decoiled, cutted, and then again rolled to the diameter that is desired. For example, in our case 2,500. With this coil, hot rolled coil steels, we will use the advantage of this memory that is already in the steel, and also it's more affordable. The price wise is more economic. The type or the grade that we will use is ST37. The old name, the new name is, we can find this with S235, or based on the DIN is 1700. Or once we're simulating or designing this in our SolidWorks, we will select a STM A36. It is the closest material to the ST37 as a base material that we will consider in our design. Perfect. Again, since we are designing these elements for manufacturing, we need to also consider something about the grinding, the welding. These are the things that later we will make the detailed documents, how we will have the welding, the sequences, or what we need to consider from the standard point of view. But let's have a quick overview of what we can already show in our design. So first of all is the grinding that we need to do on the edge to make the bevels or the chamfers for deep root welding on the meeting edge once we finish the rolling. So what we will do, we will first cut one piece of the sheet paper up to the length of close to 8,000 millimeter. Let's exactly 7,935.2 millimeter. This can be done by plasma cutting system, or with the CNC cutting system, or any simple torture. And then we need to, why we are a little bit considering extra lengths close to 100 millimeter, because after rolling we will end up with flat ends on both sides. These flat ends are the areas 50 millimeter, close to 50 millimeters on each side, that we will cut and drop it after finishing the rolling to have perfect diameter and curve in the meeting surfaces or the edges of the cylinder. So for doing this, we are considering 50 millimeters, as I mentioned. Then on the edge, we need to consider the chamfer 30 degree against the normal line to the surface that is shown here in this schematic diagram. We will consider 1.5 millimeter as a root land. That is the minimum thickness. Here we are considering it should not be sharp. It should have a certain surface to help for better heat transfer and the best penetration of the welding to have the best welding in that spot. No matter what type of welding we're considering, we might consider MIG or normal welding with the electrode, but based on regardless of that, we should have this geometry for the grinding. And the distance, we also will consider a root gap 1.5 millimeter between two meeting edges because this will help to have the best penetration on both sides once we are welding from one side. And once the meeting surfaces are fixed with a certain spacers in place, then we will have a V-shaped groove 60 degree that it's pointing outward, and we can start welding here. Definitely we will have tack welding first to fix the position of the leading edge together, and then we will start welding together. Perfect. Here we will review what is the consideration for the welding, like general numbers that we need to know. The root face or the root land is 1.5 millimeter at the bottom base of the plate that I already mentioned. The root gap will be 1.5 millimeter that we will put the spacer in between once we are fixing the parts together, and then we will start tack welding. Tack welding, we should not start exactly from the very beginning of two meeting edges, otherwise it will destroy and cause distortion or breaking or causing micro cracks there. It should start somewhere close to 10 or 5 centimeters minimum from the very beginning or very end of this shell. Then every 200 or 250 millimeter, we will implement a tack weld that should be in a certain length. It can be 20 or to 30 millimeter. And then once we have all these tack welds, we are ready for implementing the full welding on the seams. This is the thing that we will continue for all we will repeat for all the rings. Perfect. Once we finish the welding of all three rings for the cylindrical part of our silo, now we need to also welding these segments together. We should make sure that we are not aligning all the welding seams in one direction. Otherwise, we will face the very weak spots, especially when there is a crossing line of welding between the rings and between the meeting edges of each cylinder ring. To avoid that, we will rotate each ring against the other one. In our case, we have three rings, so 120 degree is the best maximum possible angles that we can consider between the rings to have the maximum distance between the welding seams. So to do that, once we are designing in SolidWorks, we are considering the first ring at the angle of 0. For example, the front face will be parallel to the front face of the assembly region or media, and then the second ring will be with 120 degree angle, and the third one will be 240 degrees comparing to the very first ring. Here we are making sure that we have the maximum distance between all rings, and the welding seams are having the maximum distance with each other, between each other. Perfect. Now we will initiate the design in SolidWorks. this is by presumptions that are you already familiar with the SolidWorks. So here we are not to train how to use the SolidWorks software from the very beginning or from scratch to do something, because here we are mainly focused on the design for manufacturing. So by this default that you are already familiar with the SolidWorks software, I'm quickly checking the main steps, how you're designing this equipment in the shell side, and then in the next episode we will add more details to that once we are ready for manufacturing this equipment. So to have the shell, first we are starting by drawing a circle 2500 in diameter, and then we are extruding. Good. Then I'm using the extrude command to extrude this 1.5 meter in the height, and the thickness is 5 millimeter for this element. The 5 millimeter thickness is according to the thing that we considered at the beginning of this slide. Perfect. Now we need to also implement the 1.5 millimeter root gap that we already discussed about, that is important for the welding considerations. We will make the documents for the welding, but I also would like to have and see exact dimensions for the welding spots or welding zones here in my design. So I'm just drawing a cutting rectangle here, 1.5 millimeter in the thickness from the center, and then I'm implementing the cut command. With cut extrude, I will cut all through of this ring that I generated already, and then this gap or the root gap is already generated. Here I use the measurement tool for measuring to make sure that 1.5 millimeter gap already implemented there. You see that it's exactly as it is there with the measurement 1.5 millimeter, the gap, I have it there. Here then I'm implementing the chamfers or the bevel grinding. So since I will consider 1.5 millimeter, the face or the land root diameter there, I'm just putting this aside, and then from the remaining, that is 3.5 millimeter, 1.75 millimeter on each side, I will implement the chamfer or the bevel grinding. 30 degrees the angle of this bevel or chamfer against the normal line to the surface of the plate, and this is as it is implemented, and you will see the grinding how it look like now. It's repeated for all four lines on the meeting edge of two plates, and here we can see it's in a better shape, and this is one perspective how it look like now, the ring that we generated. We should implement the same chamfer and bevel grinding on the other edge, one where the two successive rings will meet each other, or where we will connect the bottom conic object or the top roof deck to the rings. This is the thing that we will also implement. The same angle, the same thickness is implemented, and here we can see how it will look like. Now we have one ring. I allocated the material ASTM A36 steel, that is the ST37, and the weight of this, or the mass of this object, will be close to 462 kilograms. So for each ring we need to consider something close to half a ton. Perfect. Now we are continuing by adding the second ring to the assembly. So we are bringing the first generated ring into the assembly. We are creating a new assembly. We are just make all the mates for the first ring to the origin. So the origin of the first ring will be completely coincident to the origin of the assembly. And then we are bringing the second ring. As you see, I am considering 120 degree angle between the front plate of the second ring and the front plate of the base ring. The distance between two rings should be, with this consideration, we need to have 1.5 millimeter distance between two meeting rings for the penetration of the root welding. To do so, we are considering 1.5 millimeter distance between the top plane of two successive rings, first and the second. Perfect. This is how it will look like after just assembling two pieces of rings together. Now we are bringing the third ring. Here you see that again, I'm considering the distance 1.5 millimeter to consider this 1.5 millimeter gap for root welding. That should be the distance between the two rings on the meeting edge. And then I'm also considering in the next slide the angle between the very first ring and the last ring, or the third ring, 240 degrees. Now we are making sure that there is a maximum distance of 120 degrees between all welding seams between these three rings. Perfect. This is how it looks like after putting these three rings together. I just add one mannequin beside this shell. This mannequin is also a thing that I designed it just to have it as a signature for my designs. It's not really perfect, but it's a signature. But then you can now see how it looks like comparing to the standard human scale. This is the last slide for this presentation, and the end of episode 1. In the next episodes, we will add the other parts very quickly. We will have one silo with full all details ready for manufacturing. Let's design for manufacturing together. If you're a manufacturer, an engineering student, or an industrial designer who wants to analyze, simulate, or modify the 3D CAD model that we built today together, please just hit the subscribe button and comment the word CAD below. You will receive the link to download it. Please also comment what is the next equipment you want to see engineered. Thank you very much for engineering with me today. I'm Dr. E, and see you in the next breakdown.